Age is not a problem. I'm not one of, in other words, I'm not one of those women who hides my age. I don't really care.
How does this pronounce? Tuscaloosa?
Tuscaloosa.
Tuscaloosa.
Yeah,
Okay.
think of the C as a K.
Tuscaloosa.
It's a Native American name. There was a Chief Tuscaloosa who was the head of the, I think it was the Cherokee Indian branch that was based out of Tuscaloosa. Of course, before the Trail of Tears, but we name ourselves after them.
All right, let's go ahead and get started. Good morning, everyone. Happy Valentine's Day. So today's speaker is Dr. Sevgi Gurbuz. She received her BS degree in electrical engineering with minor in mechanical engineering and her MS degree in electrical engineering, all from MIT, and her PhD degree in electrical and computer engineering from Georgia Tech. Afterwards, she worked as a radar signal processing research engineer with the US Air Force. And more recently, she has been an assistant professor and then an associate professor at the University of Alabama, Tuscaloosa. Since January, Dr. Gurbuz has been an associate professor of electrical and computer engineering at North Carolina State University. Her main focus of research lies in the advancement of RF-enabled cyber-physical human systems, radar signal processing and machine learning algorithms to address the challenges of robust, accurate human micro-Doppler signature analysis, automatic target recognition, and control of CPHS for automotive, health, human-computer interaction, and defense applications. She has pioneered radar-based American Sign Language recognition, for which she was awarded a patent in 2022, and is developing novel interactive RF sensing paradigms built upon physics-aware machine learning and fully adaptive cognitive radar that provide for unique AI ML solutions to radar perception problems. Dr. Gurbuz is a recipient of 2023 NSF Career Award, the 2022 American Association of University Women Research Publications Grant in Medicine and Biology, the 2019 IEEE Harry Rowe Mimno Award, 2020 SPIE Rising Researcher Award, EU Marie Curie Research Fellowship, and the 2010 IEEE Radar Conference Best Student Paper Award.
Thank you very much. I appreciate your kind introduction. Yeah, so that summary already summarized the talk. So as the title indicates, I'm interested in developing radar systems for the purposes of enabling novel advanced cyber-physical human systems. Just to augment that introduction, I want to state that this is a highly multidisciplinary field. And I think you're going to find, regardless of what area that you're studying in this room, that there's a little bit of something that everyone can find in this topic, because it's an interdisciplinary topic. I myself lucked into this topic by being somewhat random and disorganized in my own pursuit of education. I applied to college to study biology, spent freshman year studying aeronautics, did mechanical engineering as a sophomore, which is what resulted in my minor, before finding electrical engineering and circuit analysis, only to luck into the topic of radar by order of the US Air Force, because I was an Air Force ROTC student at the time and then got assigned to the Air Force Research Lab. But after 20 years, I'm still doing radar. And it's in part because I've been able to find so many unique, interesting applications that's highly multidisciplinary with so many fields that I think I've always been able to find something that I can get curious about, excited about, and think about in terms of new things. So I want to kind of go back a little bit in history to kind of motivate and give context for this research area. You know, radar first emerged out of the United Kingdom's defense against Germany leading up to World War II. And at that time, when trying to develop air defense systems and trying to figure out how we could detect and find aircraft before they attacked, we developed these, or the UK at that time, developed these really large networks of antennas, one of which I'm showing you here on the left, which was known as chain home. So we're dealing with massive systems, which are large at the scale of a building or larger. It was only in 1935, actually, in a communication with the US Navy, that the term radar was coined as an acronym for radio detection and ranging. And since that time, of course, we don't really think of radar as an acronym anymore. It's taken on a definition of its own. And we've been able to do a lot of exciting applications, whether it be space satellites for remote sensing, land use management, or these ginormous antennas that we have for trying to track objects in space, like space debris, or military applications such as aircraft detection. So in 1938, aircraft detection systems were these multiple towers spanning kilometers. Now you can have a rotating antenna mounted on a vehicle, which can accomplish the same task. And as time goes forward, the radar systems are getting smaller and smaller and smaller, culminating with the first solid-state RF transceiver, which was built in the early 2010s. I think one of the seminal papers came out in 2012. And from my research, that really is like the watershed moment, in my opinion, because now the implications of being able to have a radar system that is the size of a quarter is that radar can now be everywhere. So I challenge you, sky's the limit. What do you think we can use radar for? Believe me, there's somebody who's working on it or trying to make it happen. This chart is kind of my taxonomy of what I think the major areas where people have done research in so far. It started by thinking about security, border control and security, our own border, the US-Mexico border, or other war zones where you're trying to detect whether there's guerrillas, terrorists, or other kind of insurgents who may be penetrating your perimeter. This was the military application. So this is the very first application that got started with a lot of military input. I remember 2002 as a lieutenant being ordered to just go run in the woods and try to hide. Supposedly I had advanced technical training as an engineer. Not the case, but I was the best thing they could find, my friends and I. And so we ran around, and then there was this radar engineer, you know, a much older civilian nerd who was basically trying to find us with radar. And after the whole exercise, he smirked, and we said, well, did you see us? And he's like, yes, I did. And then it was, of course, classified top secret. But like so many technologies, including GPS, this has civilian ramifications. And the applications are only growing in terms of the civilian field. So remote health and telemedicine, heart rate and respiration, determining whether someone has fallen or not, emergency response based on falls. Or some of the things that I'm more interested in are things like fall risk assessment, trying to do more advanced gait parameter estimation so we can determine, let's say, the early onset or detect the early onset of neuromuscular and other disorders. This all fits into the context of assisted living because ultimately we want to try to prevent these types of catastrophic outcomes, which, especially as you get older, results in subsequent problems that can actually shorten your life, or this time require you to have in-home care. So these are all quality of life applications. And then from there, it's grown to thinking about smart environments. You know, what if I could do a gesture instead of having speech? What if I can do a gesture to turn my lights on and off, or control the temperature of a room, or think advanced medical robotics? Let's say you had an asthma attack. Maybe the environment can detect this and your little friendly robot is going to come bring you an inhaler. So all of these things are examples of cyber-physical systems and how RF sensing can contribute to it. And human-computer interaction is a burgeoning field. Over just the last, I think the first paper came out about 9 years ago. Since then, there's been work in trying to do non-contact control of functions of the cell phone. Google was the first to kind of pioneer that chip, putting it into their Google Pixel 4 so that you can use some of the cell phone functions in a non-contact way. And then, of course, as mentioned in the introduction, I've been working on sign language recognition. The applications are blowing my mind. You know, I got first started out at MIT. My first exposure to human behavior analysis was the MIT Media Lab, which is just like the hotbed of all sorts of crazy, zany ideas of how you can use technology. When I was a student, there were Ph.D. students there working on what we now know as Google Glass. It evolved from that, and they would walk around like cyborgs, wearing like computers embedded in their glasses or mounted on their glasses. And these are other kinds of ideas which I think is along that same vein. We always think of radar as being a non-contact technology, but why not wear it? It can help you with blind navigation and provide, even on a personal level, other types of sensing capabilities, situational awareness capabilities. Lip reading with Wi-Fi, that totally, when I saw this paper, blew my mind. I'm like, really? I'm a radar engineer, and even I was like, what, really? We can do this? What about voice recognition? We actually have a faculty in the CS department here who's worked on voice recognition with radar, which is really cool. And then emotion recognition, which is more broadly known as affective computing. The idea that we want computer systems to understand our emotional state because that can better help the system respond and interact with us. So why radar then? I mean, a lot of this work in affective and other computing has been done using video or other types of wearable sensors. Why in the world would we possibly want to use radar for these kinds of applications? And I kind of on purpose, this is unfair to the wearable community, I kind of on purpose picked the most grotesque wearable image I could find for this slide to kind of make the point that wearables can sometimes be inconvenient, although obviously they're a wonderful thing, and I use a Fitbit all the time. But you don't necessarily always want to wear something, especially if you're in your own home and you just want to kind of relax and be chill. You also don't necessarily want to use video, right? Video is another one of those amazing technologies that we're even using right now for our remote guests that enables us to communicate and helps our life. But if you want to have something that's on 24/7, maybe you don't want to have a video on in your home all the time, especially in your bedroom. That's not really something that we would want. So simply by virtue of being non-contact and not recording your face, your clothes, your body, your environment, your Van Halen poster in the back of your bedroom, it offers some increased privacy, cybersecurity considerations aside. And this has been kind of the driving motivation for, I think, a lot of the radar applications and a lot of what the technical term would be radar-enabled cyber-physical human systems. So what is a cyber-physical human system? It is a system that involves two components that are interwoven with each other, sensing and control. We try to use radar signal processing, electromagnetics, physics, AI/ML to sense and extract information about what a person is doing in their environment. In response, we want the system to respond to it and take some kind of action. So, example, if you have a radar in your vehicle, which is doing driver monitoring, let's say you suffer a heart attack, what would the response be? So perceiving the heart attack would be the sensing part of the problem. The control part of the problem might be to now take an action. What should the car do? Maybe it pulls over safely to the side of the road. Or occupant left in the car detects that there's a child there. Maybe it automatically rolls down the window so the person doesn't suffocate. There's also these kinds of applications for health. I gave the example of health robotics before. And in the context of sign language recognition, as you'll see through the presentation, we're working on the design of smart deaf spaces. So we need to think about not just sensing, but also control, and also what the implication of our sensing predictions are on the control system. So I want to start, though, by just talking from ground one. What are we trying to perceive? What are the challenges? How does this impact the way we do our machine learning networks design? Humans are very complex. Maybe that's the other reason why I'm still interested in this field. It's person-specific. Gait is a biometric. How many times have you experienced the case where you see someone walking very far away, and even though you don't see their face, you kind of know it might be your friend Bob because he has this little wanky gait? Person-specific. So how can we personalize our AI/ML algorithms without relying on the sensor being on the body? This is an area of open research. Of course, sensing environments are very dynamic and highly variable. We know that people's behavior themselves are very highly variable. But not just that, the environment is greatly variable. the types of sources of RF interference you might see, or physical interference and obstacles that may be in the environment are highly variable, and to enable a robust system, we need to be able to respond to and take those into account. Of course, as I mentioned before, people can be highly emotional. They're not going to behave in the way that you predict. Last year, we went to Gallaudet University to pilot test one of the systems I'm going to talk about a little bit later for interactive sign language recognition, and the participant forgot one of the words that was in the dictionary to control the game that we were having him play, and so he started signing in Romanian. Apparently, he was a Romanian immigrant and started signing in Romanian. So I didn't think that was going to happen, but now I know the next time I design a system, maybe I should take into account more foreign languages. People do unpredictable things. Also, we have information about how people move simply because of biomechanics. So one of the popular, I think, views within computer science is to just treat data as data. And if you want to get a better prediction, what do? You just have more data. So millions and millions of samples. The world in which I operate in, I have no samples, or very little samples, because collecting data from people is difficult, it's time-consuming, and we're going to talk a lot more about data collection during this slide, but the point is if you don't have a lot of data, the only way to really get around it is to try to take advantage of what you do know, which in this case is principles of RF backscattering and biomechanics. So, open technical question, how do we take advantage of that knowledge when we're designing deep neural networks? And then finally, when we think of things such as sign language recognition, again, we need to recognize that motion is not just motion. Different gestures and different movements mean different things in different cultures. And there's a lot of language artifacts that actually we can observe in the RF data. And part of what I want to do today is to kind of focus on this sign language problem as an example cyber-physical system and show you some of the different ways in which the complexity of the human signal is revealed in the data. So in order to do that, we need to start at square one, because I expect nobody here already knows anything about radar. Maybe you've had experience with police radars, which is not a positive experience, but let's hopefully have a positive experience here today. There's three main variables that we can measure with radar. By measuring the round-trip travel time, we can determine the distance between the radar and an object. We can use the principle of Doppler shift to measure the velocity. And here, the important thing to remember about this equation is that the velocity is proportional to the Doppler shift. Later on, when I'm showing you some images where I've labeled the frequency axis, I want you to keep that in mind, that the velocity is proportional to the frequency. And then finally, if you have a multi-channel radar, then you can do things like direction of arrival estimation and multi-channel signal processing, array processing, to estimate the angle or the direction that the signal is coming from, whether it's in azimuth or elevation, based on how you've designed your antenna. Fundamentally, the data that we get from a radar is a complex time series. So IQ data. And we apply radar signal processing techniques to generate computed images or computed 2D and 3D structures. And on the screen here, I've shown you some of them. Some of the most commonly used ones, like the microdoppler signature, which shows you the velocity as a function of time, is perhaps the most commonly used data representation. But in addition to that, you can have images of range Doppler, commonly known as range Doppler maps. And if you take a range Doppler map as a function of time, you can build a 3D radar data cube. You can look at range maps, which plots for you the range as a function of time. Or you can take sliding window sections of the microdoppler and stack them to form a 3D data representation. Or finally, on the right-hand side, we have point clouds, which is what you would get if you applied a target detection algorithm onto your data and just labeled the points where you had backscatter that was greater than some threshold. So all of these, you can find papers that you do human activity recognition using all of these data representations. And now you may say, well, which one is the best? And the answer is, well, it depends. It depends on how much time you have to do the computation. If you're doing something which is in a cyber-physical system, one of the important constraints is real-time feedback. So you might not have a lot of time to use a really high-dimensional data representation, both in terms of doing the signal processing to compute that representation, and in terms of this time having enough data to do the model training. But if you only use the direct IQ time series, maybe your performance goes down. So one of the important challenges that we deal with in my research group is, again, how to kind of try to find the sweet spots for what the best form of the data is, how do we use it, when we use it, and towards the end of the presentation, we'll have some results which kind of addresses this point. So let's try to just understand microdoppler from a moment. I talked to you about microdoppler being the most ubiquitous data representation. Here's an example of a person walking on the left, and on the right, we have someone picking up an object. So I labeled the left axis as frequency, but really to be more precise, the center line is the 0 frequency point, meaning that the person is stationary. Above that line is positive velocity, below that line is negative velocity. What does negative velocity mean? It means instead of moving towards the radar, you're moving away from the radar. So if we think about what happens when we walk, you will have some movements where your leg is moving towards, and others where, relatively speaking, it goes negative because it feels like it's moving backward. And so these oscillations that you see are due to the leg movement. Meanwhile, the torso represents our largest surface, and so you will get the peak response from the torso, which usually in most applications is some kind of sinusoid. We can also see things like when you pick up an object and you can see different parts of the body moving towards the radar, away from the radar at the same time. And the whole advent of, or point of using pattern recognition and machine learning techniques on this data is to this time recognize the different patterns. Because if you can recognize the different patterns in the data, that will then cue you in on what activity the person is doing. This also holds true for American Sign Language. And in hindsight, I wish I would have split this into maybe 5 different slides so we could focus on one image at a time. But I'm going to move slowly from left to right in trying to interpret these images for you, because I found it very fascinating when I was first starting to work, especially with sign language, that there were a lot of things that we could just observe from the data itself without even relying on a deep neural network. So first of all, if you look at the data, I can tell you whether it's a person who's doing some gesture with one hand or if they're actually doing a sign with both hands. And the way that you can determine this is because if someone's moving with just one hand, then you will find that you can draw a function over the peak target response, which is a 1-for-1 functional mapping as a function of time. Whereas if you have more than one hand moving, then now you get simultaneous movements in positive and negative Doppler at the same time, and you don't get this kind of 1-for-1 correspondence. So we can determine handedness. Actually, in some of our work, we've even used handedness as a task within a multitask learning framework to improve classification accuracy. We can also determine what the orientation of the hand is. So if we take a look at this middle image for the word drink, the drink is just done like this. So when you start out with the first peak, you get a stronger first peak because the surface of your hand is towards the radar. Then once you've rotated, you're only getting backscatter from this cross-section, and that means that the power is less. In contrast, if you look at breathe, your hands are always moving back and forth to the radar like this, so you can see that there's a higher overall received power from the signal. We can count motions, so something like knife, where you're doing something like this and swiping your fingers. We can count how many times that you've swiped your fingers. And we can also look and see how the signal changes based on the direction of motion. Since radar is sensitive to radial velocity, if you do something like this by saying help, you'll see that the total velocity spread goes down because your radial velocity is lower. And we can also see the similar effect when you have occlusion. So something like right, usually they'll do it relative to the left hand as a reference. Depending on the position, you may find that your left hand is actually blocking the movement of your right hand, and that also affects your Doppler spread. So all of these things are things that we can observe. And I was also most fascinated to see that, one of the most common artifacts of speech processing. So if there's anyone, is there anyone out here who does speech processing just with voice? No? Okay, well, in speech processing, one of the biggest challenges is something they call co-articulation. And it's the idea that the way vowels sound phonetically depends on what comes before the vowel that's being enunciated. And if you look here in this signature where I've shown the velocity versus time for the sentence, wrong you, meeting starts time 2, you tell me noon, that's kind of just like the word for word transliteration. You'll see that the word you comes in twice. Let's see, you can see my arrow here and here. But if you look closely, this first U has a more distinguishable slope than the second time, and that's because when you're first starting the sentence, your hands are in a downward position. You start doing this, you have more motion, whereas in between a sentence, you're able to transition there more quickly. So you can see that the shape of the signs will change, depend on its position with the sentence. And that's a linguistic property that's true of all languages, spoken or gestural. There's other aspects of the signal that we can find too, because we started doing this work in COVID. We had a case where we had collected some participants from fluent signers, and then COVID hit, we couldn't get data from anything anymore. So we thought, well, what are we gonna do? We're just gonna sit here bored and wait for the pandemic to pass? No. So we started collecting data on ourselves. This is actually something quite commonly done if you look at like Y5 papers. People sit there and collect data on themselves, but that's actually a pretty catastrophic thing, because if you look at how the principal components distribute, just even looking at two principal components, you can see that if I'm doing copy signing, meaning that I'm a hearing person who's trying to imitate or replicate the movements of an actual sign, each one of those colors represents a single sign. And you can see just from the fact that they're like circular groupings that they tend to clump together quite nicely, which means that if you try to classify or benchmark any algorithms on imitation or copy signing, you will completely overpredict your results, and it will be a lot easier than otherwise. So for those of you working in AI/ML, you probably know that if you ever get an over-optimistic result, you should really have the warning signs flash and wonder, why is it doing so well? I remember in 2018, there was one paper that claimed to classify 300 signs with just a 9-layer CNN, and it was like groundbreaking. Like nobody had ever done that many signs before, and the performance was so high. But then you look at how they collected the data. Well, they collected all of it on themselves. So I can believe that. If you collect it on yourself, it's very easy to classify. Why? Because of memorization. This is another impact of just the human signal. If you don't know the word, what do? You try to memorize it. And when you memorize it, every time you repeat it, the variance between each repetition goes down. And this makes, therefore, all of the signs clump together. On the right-hand side, you can see how those groupings would change for an actual fluent signer. And of course, I mean, try to pick anything out in that, right? That's the real challenge on the right-hand side. How would we classify that? And so you could actually, even with something like support vector machine, you could build a classifier that tells you what is the fluency level of the speaker. Is it someone who actually speaks sign language on a daily basis, or is it an imitation signer like myself? And this is an example of just the performance gap that I was talking to you about. If you compare what you would get by testing your data on imitation signing versus using fluent signing in the training and testing, there's a 20% gap over 20 signs on one of the studies that we did during that time. So we've talked a little bit about the complexity of the behavior. The next step is to really think about how we would actually build a model for radar-based sign language recognition. And remember, one of the biggest problems is just that we don't have a lot of data. You know, unlike computer vision applications where maybe you can just go on the internet and there's databases like ImageNet that have millions of images in them, there are very few databases for radar data, and more likely than not, it's not going to be the classes that you're looking for. So we have problems just in terms of the quantity of data. We have to actually call people into our lab to collect the data, and we also have problems in terms of quality. So in one of the earlier slides, I mentioned the fact that we did radar signal processing to compute these images. Well, the consequence of that is that the pixel-wise correlations between the images are not the same as what you would see from an optical camera, right? You're getting radar data in terms of distance, velocity, angle. And if you just try to do data augmentation or other techniques by just like rotating the image, you'll get something that's completely bonkers and kinematically impossible, which actually totally destroys your performance. So a lot of these computer vision-based techniques, which use things like rotations and flippings and other things like this, they actually harm your performance when you apply them to radar data. So there is an open question then of how can I actually train the best models when I have very limited or no data? And the answer to that question is by using generative networks and simulations, and also how do we deal with real life? So there's a number of ways that we can try to train models. Transfer learning is one idea where you just take data from a different source and then try to adapt it to your data set. And we found that this has some benefits when we're using it to radar data, but it's always quite limited. It never gives you the best performance. Alternatively, you can try to simulate your own radar data, or you could use generative learning. So without kind of getting into the weeds of the radar models, I just want to kind of stay a little bit conceptual here. How can we simulate radar data? Well, if I have any animation of a person's body derived from motion capture data or something like this, I can use radar models and the radar range equation to calculate what the expected radar return is, to animate the points in time, compute how those relative distances vary with time, and using this equation, we can get like a very crude kind of representation of what the microdoppler and what the complex IQ data for the signal should be like. One thing that we've done, which has been really helpful in terms of data augmentation, is instead of trying to do rotations and flipping for data augmentation, we apply data augmentation to the skeleton itself, meaning that you can stretch the skeleton both in terms of slowing down and speeding up, as well as the size, and then applying perturbations on the trajectories. And we found that this really helped us to just take a very few number of measurements. So we took 55 mocap measurements across 5 students, used this kind of diversification to generate a database of 32,000 signatures, and that allowed us to train a 15-layer neural network, which at the time gave us the best performance of any of the other networks that we had compared. And oh, by the way, at the time we did this work, it was customary to only classify 3 or 4 human activity classes. So the fact that we were going so deep and that we were doing so many activities was pretty unique for its time. Of course, since then, now we do a lot more things than this. But the alternative is to try to use generative networks. And here I'm trying to illustrate to you what the principal problem of generative networks is. Namely, the fact that generative networks have no understanding of the underlying physics of motion, and therefore they generate samples that might visually look plausible, but kinematically is impossible. And my favorite one is this one here, next to the falling label, because you'll see that there's both positive and negative velocities. So essentially what this would physically correspond to is you're getting split in half, and half of your body falling forward, and the other half falling backward. That's the physical meaning of this signature. It's not possible for it to happen. And if you train your neural network with it, again, it will degrade your performance. And so what we've done is play around with different types of kinematic sifting algorithms, where maybe we use GANs to generate a lot of data and to try to sort through which samples are really based on physics impossible and throw them out. And it's kind of fun to see, because the more you throw out, the better you do in terms of your classification accuracy. But of course, just building a filter to sift out bad samples doesn't really solve the problem. What we want to do is design a network that from the beginning does not make those mistakes. And this is where I find the idea of physics-aware machine learning so powerful. Because if you think about what your goal is here, what is the goal of simulations? Based on high-fidelity physics, which is a high degree of knowledge but no data, you're trying to represent your signal. And maybe this represents, therefore, very fundamental properties. But as we know, when you go in the real world, everything is dynamic, everything is changing. If you use a model that doesn't have anything that's specific to your current time, you're not going to be able to capture any of the sensor-specific properties or the environmental properties, which will also be affecting your signal. This is where having data comes in, but maybe not a lot of data. Our goal is to try to develop techniques that uses physics as well as data, some data, reasonably simple physics-based models, to get better performance along a wider range of scenarios. And so I just, for this talk, kind of picked one example among all the things that we've done, which is, to try to fix this problem with the GANs, how can we inform it about what some of the limitations are of what it's doing? And we thought, well, think about the envelope of the microdoppler signature. That represents your maximum speed based on just physically what your body is doing in terms of its motion. So if we can compel the GAN to conform to the envelopes, then we'll avoid some of these problems of like the body splitting in half, right? So what we did was we extracted the envelopes from the data that was generated, and we supplied it into the auxiliary branches of a discriminator, and basically included in the cost function another term that is what is broadly termed just the physics-based loss. And so this formulation you'll see in a lot of places since then. It shows up in a lot of places where people are trying to develop physics-based loss terms to try to capture the non-statistical differences between the samples. And so we looked at things like dynamic time warping and other ways of looking at the matching of the envelopes, provided that into the loss term, and we did a lot better. So just visually, let's look at the eye test. In the left column, we have real data samples. In the right column, we have the result of our physics-based GAN. And in the middle, we have like just a standard Wasserstein GAN with nothing special to it. And if you start by looking at the middle column, you'll see that in no way do conventional GANs really are they able to represent the periodicities which are traditionally associated with ambulation, right? Walking is a periodic movement. You need to be able to see those periodic velocity changes in the signature. You get wispy things. You'd almost like look at it like a gas, not a person walking. Whereas if you look to the signatures to the right, they're very close. The first time my student showed me these results, I kind of looked at him and I said, are you sure you didn't copy and paste mistakenly? And I actually ended up like zooming it and looking at like a pixel by pixel level and said, oh, okay, the samples are indeed different. So I know you might be thinking I copied and pasted. Seriously, I didn't. But that's how good results we were able to get. And if we apply this data then to sign language, we discovered that we got the most amazing performance, the highest performance out of using a small amount of fluent signing data to this time drive a process where we use this physics-based GAN to generate training data. And then we were able to get all the way up to 100 signs in terms of classification. In this particular study, we also tried one other thing, which is since it's a lot easier to find hearing people around, we thought, well, we have all this data on ourselves, imitation data. Maybe I can use domain adaptation to take my kind of funny way of signing and transform it into something that would look closer to the way a fluent person might actually sign. This is the results which are given by the Pix2Pix network here, which is a popular style transfer network. And as you can see, trying to fix kinematics by using domain adaptation does not really work. It's always better to try to synthesize it correctly from the beginning, and we've gotten the best results with this physics-based GAN. So now that we have a model, let's use this in an actual cyber-physical system. So what we did was we thought, okay, well, what would be a good environment in which we can kind of try to pilot and play around with these models? We thought chess game might be good because it was pretty popular with my high school kid at the time. And it also is a game that doesn't really have strong real-time requirements, right? Chess players are kind of used to waiting around. So if we have any lags or latencies in the process, the game kind of takes care of it for us. And the way that this would work is that we basically have the person click on the piece they're gonna move, and when they click, it shows the possible moves, and on each one of these squares, there's a word which is written, and if they sign the word, then the system will recognize their signing and it will move it to that space. And so when we first did the data collection, we used video recognition to control gameplay. Once we collected a certain amount of data, and from both video and radar, we were able to get that radar data and train a radar-only model. And then the second time we went and had participants play with the game, we actually had the radar system itself control the interaction, even though we were still recording both radar as well as video data. And if you look at how we did, this is kind of cool. So Gisler is a Google model for sign language recognition. It's been pre-trained on ASL samples that they've collected, like millions of them. And the important thing to see here is that it drops from their own training to our own data from 92 to 48, whereas our model drops from like 100% if you're using the physics-based GAN, all the way down to 9%. So in the real world, all of the models died. And because we're getting short on time, I'm gonna kind of skip through some of these slides. But essentially what these performance comparisons are showing is, you know, if you try different ways of using the directed data, whether or not you use ImageNet pre-training or not, essentially what we found is that the directed data didn't really help. I think for me, the most compelling result is if you compare this black line, which is the result of just using transfer learning, with this purple line, which is where you're doing ImageNet plus the physics-based GAN. You can see that once you've acquired about 20-25 samples per class, there's no difference in the results that you get from having this huge database of controlled experiment data. And so I'm going to talk in a little bit about the differences between natural and controlled data. This is kind of like my last data point, which again also shows the same point, which is that on this data set, we got the best performance when using the physics-based GAN, trained using natural signing data. And ImageNet definitely helps in terms of pre-training. All the databases that we had collected during COVID and other times from fluent signers who came into our lab and just did the signs that we told them in that type of a controlled experiment, none of that data was really worth the time, money, or effort to collect. And this is really kind of now the theme, like where I'm trying to also convince people in my community to kind of abandon this idea of controlled experiments, because radar engineers still do. 99% of the publications are all in controlled environments. The participant comes into the lab, you tell them exactly what to do, how to move, what to say. The participant does those movements, models are trained, wonderful performance is achieved. But as you can see, if you just put the person in the wild, the only difference being the difference between the chess game and the directed experiment. One, the person thinks that they're just playing a game. In the other one, the person's like, oh, I'm giving data, so now I have to, they ask like, how should I sit? Can I put my hand here? Should I do this? Should I do that? They're very self-cognizant. This is what's known as the Hawthorne effect. The idea that in different conditions, if a person knows they're being observed, they behave differently. But if you say, oh, just come and play this game, well, then they act as they normally would. They would slouch, maybe they put their hand over here, they scratch their head or talk Romanian. They can do whatever they want. And of course, then you actually see how the sign language is actually articulated. So again, we've done a lot of work trying to this time address real world behavior. And it's not just about how you collect the data. It's also about, not requiring people to walk in a straight line anymore. Again, 90% of the papers require their participants to walk in a straight line. And it's like, nobody moves that way. You can publish a lot of papers. You're not going to solve any real world problems by doing that. So this is an example of a microdoppler signature, which actually has transitions and actually shows you the connectedness between different activities. And the thing to kind of understand here and why there's still so much work that has to be done in terms of integrating biomechanics is that you can't just crop or put vertical lines that segment this data into one activity to another activity, because there's a transition region. Our body doesn't instantly go from one position to the next position. There's a natural transition in between it. And if you really want to be able to understand what somebody's doing, you have to be able to characterize those transitions. And some of these transitions actually are medically relevant transitions too. Like if you go into a physical therapist's office, they'll ask you to do what's known as a tug test, time up and go test, where you walk, you sit down and stand up. And there the physical therapist is trying to characterize the transitions themselves. How easily, how fast can you sit down and stand up, for example? So we're trying to develop algorithms that will allow us, using biomechanics, to capture the entire phase of walking, including sequences. And this is also true for sign language. It's great to build a model and put it in a chess game, but ultimately what we want to do is we want to have something which is really the equivalent of an Alexa or Siri. You put it in the room. If a deaf person wishes to interact with that personal assistant using sign language, we need to be able to understand when the person's in the room, when they actually want to communicate with the device. Maybe they're just talking among themselves, or maybe they're doing dishes. We have to discriminate sign language from daily activities. And then we need to do kind of the conversion process. So we have some work where we show good results in terms of being able to do a temporal parsing of the data and then take those segments out and actually be able to this time apply our sign language recognition models. And in doing this work, though, if you look to the right-hand side, you'll notice that I have kind of 3 blue squares here, which of course is hard for you to see. So let me explain the significance of them. One of them is a microdoppler signature. One of them is a range Doppler versus time data cube, and the other is a range angle versus time data cube. So in doing these methods, we're using the complete radar measurement, and we're using 3 data representations at a time. So it gives really amazing performance and accuracy, but of course the problem is it's not as amenable to real-time applications. So in some of our more recent work, we're trying to come up with ways of really saving energy and saving computation time by changing what we are transmitting. The amount of samples that is associated with each one of those data representations is dependent upon the transmit waveform itself. How frequently are we sending a pulse? What is the bandwidth of the signal? What is the sampling rate? Things of this nature. And so what we've done is we've kind of determined as initial work 3 different modes, and associated with each mode is 3 different waveforms. The first mode, which is the presence await mode, is the simplest mode where we're transmitting something with the slowest pulse repetition interval or pulse repetition frequency, the lowest bandwidth. And the way that we're processing the data is just to detect whether someone's in the room or not. So we're not even doing any kind of radar signal processing. We're just doing energy detector type things to understand whether a person is in the room or not. In the trigger await mode, now we're assuming that there's a person in the room. The person's doing something like daily activities, but our goal is to recognize one specific sign, this equivalent of Hey Siri, right? You just want to recognize that one sign. So we have a faster pulse repetition frequency because to detect sign language, the temporal interval is very important. But then once we've detected the trigger and we know the person wants to communicate with our device, then we go to like our highest bandwidth, our fastest pulse repetition frequency, and we employ this time that joint domain approach. We're using all the radar data to this time be able to translate the signals. And what we've shown is that this approach has been effective in allowing us to manage the trade-off between computational complexity, power consumption, and performance in a task-dependent fashion, which actually depends on human behavior itself. So in kind of like our next steps, what we're trying to do is incorporate all of these other factors too. I mean, since we're engineers, I focus mostly on the technical problems. But the truth is that if you actually want to build something like this, there's a lot of other community needs and cultural factors that need to come into play. And the best example I could give you of this is the question of trigger design. It's customary in the signing community that everybody has a gesture or a sign, which is their name. Not just their English name, which has a specific spelling and which can be finger spelling, but a sign, which is their name. The only way you can get a sign name is if someone who's deaf gives it to you. Okay, so for example, I've been interacting with the deaf community for several years now. I was very, very close to getting it once. I could literally see on the girl's face that she changed her mind last minute, so I still don't have a sign name. It is one of my research goals. But when you think about a trigger, how can I, as a hearing person, decide what that trigger has to be? By cultural practice, a deaf person will need to name the system. The deaf person will need to decide what that sign is. And we will need to kind of integrate both our capability of technically recognizing whatever that gesture is, as well as work with the community to find out how they would want to use this system, how they would want to trigger the device from cultural as well as technical perspectives. And two, we need to focus on community needs. There's a lot of sign language papers which are out there stating that they want to improve the communication of hearing and deaf people. Believe me, deaf people are perfectly able to communicate and express themselves. Like any other language, if you have someone who knows German, how do you communicate with them? You get an interpreter. There's no problems in terms of communicating between hearing and deaf people when you have an interpreter. Focusing research in this area almost puts the burden on the community by saying that somehow they're deficient and unable to communicate with us, which is an incorrect perspective. The perspective that we are taking in our work is instead, how can we get technology to better serve the community? How can we design the technology to become more accessible? This is a more easily solved problem because now I don't have to understand every single thing that a deaf person is saying. I only need to understand so much as I need to be able to facilitate the interaction. And all of this needs to be done in a community-driven way to enable it. So in conclusion, cyber-physical human systems are inherently very multidisciplinary. You cannot just focus only on the sensor or only on the control system or only on your AI/ML algorithm. You really do need to think about how all the human characteristics of the data expresses itself, both in your design of the AI itself and in the overall system design as well. And you should get away from trying to do controlled experiments. It's so easy to say, well, let me reduce the scope of the problem and just do controlled experiments and get wonderful results. But none of that actually translates to the real world. And this is a problem that a lot of the video-based sign language recognition methods continue to suffer from because they as well are continuing to collect data in a controlled way. So this is not just a radar problem. This is a much more broader, I think, human sensing and sensing problem. So humans are complex. Instead of trying to avoid it and control it, we should embrace it. The more data that we collect interactively, the better we will be able to design robust systems for cyber-physical human applications. I focused this talk specifically on sign language because next week I'm giving another talk. So if you like radar, if you think it's cool, if you're just bored and want somewhere fun to be, I'm going to talk about all the health applications of the work that I'm doing at the Assist Center. So I'd just like to invite everyone to come if they are interested to do so. And I believe they also have like a web link so you can join on Zoom if you like. And otherwise, I just want to thank everyone from listening, as well, of course, all of my collaborators and funders which have made this work possible. And I look forward to your questions and comments. Thank you very much. Yes.
I was trying to get a sense of the power response of your system was.
Yeah. So the incident angle is an important parameter. And what we found is that if you kind of stay between like plus minus 45 degrees, this is just an empirical observation, we tend to do pretty well and we're still able to do some recognition. But of course, the more and more off angle you go, it's going to really lower that Doppler bandwidth of the microdoppler, and it makes things more difficult to recognize. And so if you're exactly perpendicular, you're probably not going to get, the radar is probably not going to see you. Most of the commercial radar systems that we use, they also have like about, I think, 100, 120 degrees wide antennas, or sometimes they're as small as 70 degrees. So that kind of limits your coverage from that point of view as well, based on the antenna it's connected to. That's not really an inherent radar problem. We're relying on radars that are designed for other applications. So you could design a radar that had, much more wider coverage and whatnot. But you're correct. The aspect angle is going to limit things, and you have to take that into account in your data sets as well.
Are you training at individual angles?
So one idea that I tried before was actually incorporating tracking, because if you actually track the person in the room, then you know the position of your radar, you know where the person is. You can kind of figure out what the angle is, and then do your prediction on a training database that is close to that angle, and that boosts performance. The problem with this idea, of course, is that this is done offline. So again, it comes back to the problem of how would you do something like that in real time? And currently, solutions for doing that in real time have not been proposed. So that is an open area of research. Yep. Yes? Well, we're detecting people. So when you say size, really what's important is what the backscattered power is. And more than the size, the important thing is how far away the person is. And so obviously there's very powerful radars out there. You can detect people from kilometers away. But with these types of applications, for health reasons, we cannot transmit very high power systems. So the radars that we're using, I think the highest transmitter power is something like 100 milliwatts. It's a very, very low power system, which means that for most people, you'll only be able to see them within the room. You're not going to be able to see them like kilometers off with that power, just for safety reasons. Yeah, so I've not seen any radar applications where you're detecting something at the cellular level. Yeah. Yes, sir.
How much does noise in addition to more actual long translations?
Yeah, so that's a great question. So all the work that I've done so far has been indoors. If you go outdoors, you get much more sources of noise and clutter and things of that nature. And ultimately, it comes down to your signal-to-noise ratio. And so you're absolutely correct. When your signal-to-noise ratio starts dropping, I would say like below 10 dB, then you start to see every single deep neural network out there, not just like the physics-aware ones, which I'm working on, but like every single deep neural network out there starts to fail. And the conventional way that we kind of, as radar engineers, try to avoid this is by applying on the pre-processing steps things like moving target indication and other kinds of clutter filters to denoise and remove those unwanted clutter returns as much as possible before we put it into a deep neural network. Where that becomes challenging for my applications, though, is that oftentimes the data that I have will have significant frequency components that are very close to zero. So if you're trying to detect, let's say, like a vehicle, the Doppler returns of that vehicle will be much separated from all of the environment returns. And you can see the vehicle. But now when you have them overlaid, if you try to filter out that signal component, if you try to filter out that noise or clutter, you'll oftentimes also eliminate part of your signal. So depending on the radar that we're using, we found that for some radars, we get better performance when we apply the clutter suppression. And in other radars, we do better if we just let the deep neural network deal with it, if you will, because we're losing too much signal component close to zero if we filter it out. Sure.
You see a fall off speech patterns signals are, 100 words a minute or something.
Yes.
Typically, sign is somewhere in that range, right?
Mhm.
Fall off with regard to, WPM.
Yes. So we've not worked on connected discourse yet. The primary reason being that we don't have data for it yet. So one of the other objectives in developing and focusing on developing the interactive system is because to ask like a deaf person to come in and say, okay, just say this, say that, I mean, that's not really like a sustainable model. It creates problems not just for radar, but also for video-based sign language translation as well, both in terms of the characteristics of the data and in terms of the quantity of data. So right now what we're doing this year is we're working with Gallaudet University to take one of their labs and convert it into a deaf space, a smart deaf space. If we are able to do this and hold and conduct different activities there, whether it be for entertainment like doing games, or maybe it's other kind of educational activities, then the process of collecting data won't be a burden anymore. This is something that I'm kind of acutely sensitive to because, it's kind of like you're begging the community to come in and they're like, okay, so what am I doing this for again? It's not a sustainable model. So if we have them just use the environment for something valuable and collect data implicitly, then not only will we get natural signing data, but we'll be able to connect connected discourse and then start working more towards that direction. In my opinion, I think the ultimate solution we're converging towards is not like a video-only or a radar-only solution, but a solution that uses both radar and video. We've been focusing on the trigger detection problem for radar because we think that takes advantage of the benefits of radar the most, right? Like we want to have privacy. So we don't want to turn on any kind of video camera unless someone actively triggers the device. So for ambient sensing, having like the radar-only mode operational until a person triggers the device makes the most sense. And then once the device is triggered, we'll get radar as well as video data. And so kind of parallel to this, I am working with a linguist and cognitive neuroscientist on how we can use radar to do the temporal parsing. Because this is one of, radar, video has two challenges. One is just being able to do the temporal parsing, and two, the depth perception is more limited rather than radar. So rather than doing like a blind fusion of radar and video data, we're looking into kind of in a language-based functional manner, how we can use the data from both of these sensors to enable better translation once it's triggered. So otherwise, radar only, it's a tall task. ASL also involves grammatical markers that are based on facial expressions. And that's something that currently radar is not picking up. At least the radars we're using. Yeah, great question. Yes, sir.
Are these systems also robust to like that? Because which I can imagine them to be catastrophic for particular applications.
Yes, so obviously the cybersecurity problems, like what you're talking about spoofing, that's already happening with electronic warfare, right? So this is something which military systems can fall prey to unless you defend against it, where if someone knows what your transmitted signal is, they can transmit a signal towards your radar, which makes it seem like there's an aircraft 5 miles away, right? And so all of those techniques, of course, still come to bear here, so that yes, there are cybersecurity considerations that, like all of the other sensors, need to be taken into account to ensure that the data is both protected and not used for nefarious means, as well as to prevent harmful actors from interceding. The other example that I would give, which I don't know if automotive companies, how much they've thought about this, but imagine having a self-driving car. I mean, how easy would it be to like kidnap the president if you just overtook his like self-driving capability and just had the car drive him off somewhere else, right? So all of these are really huge problems that have to be part of the total solution, yeah.
Can we also make some kind of waveform design kind of applications? Let's say we're doing active sensing specifically for science.
Yeah. Yeah, so right now we've primarily been looking at FMCW waveforms and changing the bandwidth and pulse repetition frequency. In the broader context, if you think about just how congested the spectrum is getting, there's a lot of work on trying to do radar communications, coexistence, trying to utilize Wi-Fi waveforms or design new waveforms that would avoid those kinds of confusions and contexts. So right now, since we're kind of focusing on just the most basic sensing problems, we haven't really explored other waveforms beyond what I've shown, which is just varying the parameters of the FMCW radar. But there's definitely, I think, room to kind of take a look at it in a broader sense. And at a certain point, I think it does come down to cost as well. I mean, one of the reasons why we haven't really also gone outside of FMCW is because that's the most ubiquitous, cheapest radar out there. You start getting into trying to develop nodes that transmit very specific waveforms, it's not going to be something that really translates from a commercialization perspective. And if you look at the larger companies like Google and Amazon, who are exploring radar-based cyber-physical human systems for health and interaction, all of them are using FMCW radars. And so in that sense, we want to have our algorithms translate to those platforms so that they can have a broader appeal. But those are just practical considerations. Yeah.
One more question on.
Sure.
The question says, what is the memory size, space size of an inference model?
Oh, that's a great question. Any of my students remember what Emra's model, like Kamral, do you remember how much space Emra's model took up just by chance? I know he listed in the paper, but I literally don't have the number in my head. To the user who wrote, like, if you could just send me an email, I'm glad to email you back what that number is. We have it, I just don't remember off the top of my head. Yes.
What frequency is your radar?
Yes, we're using 77 gigahertz. And then the work that we did where we were adapting the transmit mode, that was at 60 gigahertz. So we're using millimeter wave.
That make your does that even matter?
Yeah, that's, no, I mean, that's interesting. I mean, for sure we've noticed finer microdoppler signatures, primarily because if you again go back to the Doppler shift equation, the higher transmit frequency you have, the smaller movement, the bigger the Doppler shift you see. So when you go up to high frequency, you definitely have more sensitivity in terms of being able to see movement. The disadvantage, though, is that at higher frequency, you also get more atmospheric attenuation. So the higher up you go, the shorter, for the same transmitter power, the shorter your range will be. So those are the trade-offs.
When your target is like right in front?
Yeah, so if the person is sitting down and playing a game, arguably it doesn't matter. But if you're trying to do something like a smart environment, depending on your size of the room, maybe at that point it could matter. Yeah. Yeah, you're welcome. Yeah, if anyone has other questions, I have time afterwards. And I'm always here, so you can always feel free to contact me. Thank you. Thanks. So Panopto is still recording. Should I just say stop? Yeah, go ahead.